Winter is coming. Those words made famous in Game of Thrones carry more weight than just a warning about the change of seasons. In the fictional world of Westeros, winters could last for years, even decades, bringing hardship and famine. But here's the surprising truth. On Earth, long winters are not just fantasy. Our planet too has gone through ages where icy conditions dominated vast regions for tens of thousands of years. Entire continents were buried under sheets of ice, reshaping landscapes and civilizations alike. This wasn't the result of mere chance. These long winters and the warm intervals between them are driven by powerful cosmic rhythms that influence the Earth's climate over immense timescales. Scientists call them the Milankovitch cycles, after the Serbian astronomer Milankovitch, who first described them in the early 20th century. So, what exactly are these cycles? How do they affect the world we live in today? And perhaps most importantly, what do they reveal about Earth's future? Let's take a journey together into the mechanics of our planet's climate engine and explore why, in more than one sense of the word, winter is coming. Before we dive into long-term cycles, let's review something familiar: why we even have seasons at all. The Earth doesn't spin upright. Instead, its axis is tilted at about 23.4 degrees relative to its orbit around the Sun. Because of this tilt, one hemisphere points toward the Sun while the other tilts away at different times of the year. The result is the cycle of summer and winter we all know. This effect is especially dramatic in places near the poles. Take Tromsø in northern Norway, for example. In summer, the sun never sets for months at a time, while in winter, it never rises above the horizon. Imagine living through 2 straight months of daylight or darkness. Meanwhile, near the equator, the tilt makes little difference. Sunlight there is more consistent, so seasons barely change. Now you might think this is the whole story, but it isn't. That tilt, as crucial as it is, does not remain fixed forever, nor is the Earth's orbit around the Sun a perfect circle. Both are subject to slow, predictable changes caused by the gravitational pull of other planets. These subtle shifts add up, creating enormous consequences for Earth's climate. To understand them, let's step beyond everyday seasons into the realm of the Milankovitch cycles. If you picture Earth orbiting the Sun in a neat circular path, you're not alone. That's how many of us first learn it. But the reality is more complicated. Yes, the Sun's gravity dominates, but other planets, especially giants like Jupiter and Saturn, also tug on us. Jupiter, for instance, is over 300 times the mass of Earth. Its gravitational influence is enough to nudge our orbit tilt and even the orientation of Earth's axis. Over long timescales, these small tugs don't simply cancel out. They settle into cycles. These cycles alter how much sunlight Earth receives, how extreme our seasons become, and whether glaciers grow or retreat. It was Milankovitch, a Serbian engineer and astronomer, who pieced this puzzle together in the 1920s. Under house arrest during World War I, he spent his time calculating how variations in Earth's orbit could explain the timing of ice ages. His work was meticulous, page after page of mathematical tables, long before computers existed. Today his cycles are a cornerstone of climate science. But what exactly are these cycles? There are 3 main ones, and together they orchestrate Earth's climate over tens of thousands of years. Let's explore them one by one. Earth's orbit isn't fixed. Over a cycle of about 100,000 years, it shifts from being nearly circular to more elliptical, and then back again. When the orbit is more circular, Earth stays roughly the same distance from the Sun all year round. Seasons are relatively balanced. But when the orbit becomes more elliptical, Earth's distance from the Sun varies significantly over the course of a year. That means stronger contrasts, colder winters when we're farther hotter, summers when we're closer. Currently, Earth's orbit is close to circular. Still, there's about a 7% difference in the sunlight we receive between January and July. In the distant past, this difference has reached as high as 23%. That may not sound dramatic, but imagine how ecosystems would respond if summers suddenly became much hotter and winters much harsher. Such shifts in energy input can mean the difference between ice sheets growing or shrinking. If you've ever spun a toy top, you've seen how it wobbles as it slows down. Earth does something similar. Its axis traces a slow circle in the sky, completing one wobble every 26,000 years. Right now, the axis points toward Polaris, our North Star, but 13,000 years from now, it will point elsewhere, and the timing of the seasons will effectively flip. The Northern Hemisphere will have summer in January and winter in July. This may not change the total amount of sunlight Earth receives, but it does shift when seasons occur relative to Earth's orbit. In combination with eccentricity, it can amplify or reduce seasonal contrasts. Finally, there's the tilt itself. Over 41,000 years, Earth's tilt shifts between about 21.1 Kelvin and 24.5 degrees. The greater the tilt, the more extreme the seasons, hotter summers, colder winters. At present, the tilt is 23.0 and slowly decreasing. That means milder summers and warmer winters. Sounds pleasant, doesn't it? But here's the twist. Mild summers allow winter snow to survive year after year. Over centuries, that lingering snow turns into ice sheets. The more ice, the more sunlight gets reflected back into space, cooling the planet further. So paradoxically, a smaller tilt can set the stage for the growth of massive glaciers. When these cycles combine, the results can be dramatic. Over the last million years, they have coincided with the rise and fall of ice ages periods when ice sheets stretched across North America and Europe. We often imagine harsh winters as the cause, but it's not the cold winters that trigger ice ages. It's the gentle summers. Summers too mild to melt. All the snow allow glaciers to grow year by year. White ice reflects sunlight, which makes the planet cooler, which allows more ice to form. This positive feedback loop is what scientists call the snowball effect. In fact, we live in what scientists technically call an ice age right now. It began millions of years ago. The warmer period we're enjoying, known as an interglacial, is just a temporary break between colder epochs. Without it, many of today's cities might still be buried under ice. Now, you may be wondering if these cycles drive Earth's climate. Does that mean we're helpless? The answer is more complicated. The Milankovitch cycles operate slowly over tens of thousands of years, but human activity burning fossil fuels, releasing carbon dioxide and methane, has already shifted global temperatures in just a few centuries. In effect, we are speeding up what nature writes slowly. If the snowball effect describes how ice can spread, there's also a reverse snowball effect. As ice melts, less sunlight is reflected, more heat is absorbed, and warming accelerates. That's the path we're seeing today. So while natural cycles tell us that another ice age will come eventually, our actions may delay it, or perhaps bring a different kind of climate disruption altogether. The Milankovitch cycles remind us of something humbling. Earth's climate is not fixed. It breathes, it shifts, it transforms over rhythms far beyond our lifetimes. Right now, the cycles are in a phase that stabilizes Earth's climate, giving us relatively mild and balanced seasons. But history tells us this won't last forever. One day, the cycles will align to make winters harsher, summers milder, and glaciers will return. Still, the more immediate challenge lies not in the distant cycles of astronomy, but in the choices humanity makes today. Will we allow greenhouse gases to tip the scales in ways no natural rhythm ever has? Winter, in some form, will surely come. The real question is, what kind of world will we leave for those who face it?